Alright, so we're going to start our next unit on exponents and exponential functions. What I want to do before we get too far into it, I just want you guys to do a little bit of investigation here. So back in grade 9 you did a lot of work with some exponent laws, which we're going to review in a little bit. But you didn't ever really dealt too much with negative exponents or zero exponents. So what I'd like you to do here, I've given you three tables of values to fill out in three different equations. So y equals 2 to the x, y equals 3 to the x, and y equals 2 over 3 all to the exponent x. What I want you to do is put the different values of x here into each equation and solve for y. So for example, let's say we're looking at the first one and we have x equals 3. Let's say we're doing that one. We're going to do y equals 2 to the exponent 3, which we know is going to be equal to 8, which will give us that part of the table. What I want you to do is fill in as much of this table as you can, and what I want you to start looking for is different patterns that you see inside the graphs that are there. So different patterns as you move up and down the table, and see if we can generate any new exponent rules from that. Okay, so give that a try. When you're finished going through those tables of values, push play again, and you'll go through the answers together. Okay, so take a look at what we got here. Now, for some of you, when you're going through this, your calculator may have given you decimals for some of these ones that are actually fractions, but that's okay. We'll talk about how we can generate those exact fractions just by using patterns. So you'll notice here with y equals 2 to the x, as you move down the table, you'll notice that each y value is multiplied by 2. Okay, so because 1 times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16. Okay, which kind of makes sense, right? The exponent's going up by 1, so you're multiplying by 2 every single time. So that means as you go up the table, okay, you should be dividing by 2 every single time. Okay, dividing by 2 every time we go up. So 16 divided by 2 is 8, divided by 2 is 4, divided by 2 is 2, divided by 2 is 1, and then you can keep going into the negative values for x. So 1 divided by 2 is 1 over 2. Divided by 2 is 1 over 4. Divided by 2 is 1 over 8. So even if your calculator is giving you decimals instead of fractions, you can follow that pattern and get the values in there exactly. Okay, and you notice here we're multiplying by 2 as we move down the table, dividing by 2 as we moved up the table, and you'll notice that the base of the exponent here was 2. So let's see if that follows along over here when we had a base of 3. So do we multiply by 3 as we move down? Yes, we absolutely do. 3 times 3 is 9, times 3 is 27, and 27 times 3 is 81. So that means going the other way, we're going to be dividing by 3. So 1 divided by 3 is 1/3, divided by 3 is 1 over 9, and divided by 3 is 1 over 27. Okay, so for y equals 2 over 3 to the x, as it might seem a little bit early because it's fractions, but now we know we're just going to be multiplying by 2 over 3 as we move down the table. So 1 times 2 over 3 is this, 2 over 3 times 2 over 3 is that, and so on and so forth. Okay, going up the table, we're going to be dividing by 2 over 3. Okay, remember that dividing by 2 over 3 is the same thing as multiplying by the reciprocal, which is 3 over 2. Okay, so 1 times 3 over 2 is 3 over 2, times 3 over 2 is 9 over 4, and so on and so forth. You might see some other patterns as well, which we're going to talk about a little bit more later, but you might see that, hey, 2 to the exponent 3 is 8, to the exponent negative 3 is 1 over 8. Interesting. Is there a connection there? Just like you see, for example, 3 squared is 9, 3 to the negative 2 is 1 over 9. Okay, 2/3 the exponent 3 is 8 over 27, the exponent negative 3 is 27 over 8. You'll see that those are reciprocals of each other. So that, again, is a pattern that hopefully we saw when we were looking at the table, and we can use that to generate some new exponent laws. Okay, so before we get into those, though, I want us to take a look at the laws that you would have learned back in grade 9. So you may remember some of these very, very well. If not, that's okay, we're going to review them. So the first thing we have is we have x to the m times x to the n, i.e. you're multiplying two different powers that have the same base. Okay, let's just remind ourselves of what happens there. You may remember the rule, but let's just see why it happens. Okay, so let's take a look at 5 to the exponent 3 times 5 to the exponent 4. Okay, so if we were to write that out in expanded form, 5 to the exponent 3 is 5 times 5 times 5, and 5 to the exponent 4 is 5 times 5 times 5 times 5. So altogether we have 7 copies of 5 multiplied by each other. Okay, so we can simplify that as 5 to the exponent 7. So if you're looking for a shortcut here, if you look at the exponents, you would 5 to the exponent 3 times 5 to the exponent 4, which gives us 5 to the 7, means we're going to add the exponents. This is called the multiplication rule for exponents, and in this case, again, you would just add those two exponents together. Okay, for the next one, here we're dividing two powers with the same base. Again, you might have an idea of what the rule was if you think back to grade 9. But let's just say you have 7 to the exponent 5 over 7 to the exponent 2. Okay, so we have 5 sevens on the top of the fraction there and 2 sevens on the bottom. And using your rules and canceling as much as you can, we have 2 sevens are going to cancel each from the numerator and denominator there. So all in all, total, that's going to simplify to just having 3 sevens left over, which is 7 to the exponent 3. And if you're looking for a shortcut, again, the rule is if you're dividing two powers of the same base, you're going to subtract the exponents. Okay, and that's that rule right there. Okay, the third rule is what we call power of a power. Okay, so we have a certain power that's raised to another exponent. So let's say we have negative 4 to the exponent 3 all to the exponent 4. Now remember, when something's to the exponent 4, it's multiplied by itself 4 times. Okay, so what this means, we have negative 4 to the exponent 3, but 4 copies of it. Okay, and once we have 4 copies of that are multiplied, we can use our multiplication rule to say that, hey, look, the base is the same in all cases, negative 4. We can just add the exponents. So 3 plus 3 plus 3 plus 3 is 12. Okay, and again, if you're writing it all in expanded form, you'll see that there's 12 of them. But you wind up with negative 4 to the exponent 12. Could we get that a little bit faster? Well, it's by simply multiplying your exponents there. 3 times 4 gives us 12. Okay, so our last two, and these are ones that usually are the most common types of mistakes. So here we have two things multiplied together that are all raised to an exponent. Okay, now the common mistake that people tend to do is, let's say I give you something like 2x all to the power 3. The most common mistake that I see, and this is not true, is to say that it's 2x cubed. Okay, that is incorrect. It's actually something else entirely. Let's remind ourselves of why it's not going to be 2x cubed. It's actually going to be 8x cubed. Okay, that 2 gets cubed as well. So let's take a look at that one. So let's say we have 3x all to the exponent 5. So remember, if something's to the exponent 5, it's multiplied by itself 5 times. So we have 5 copies of the 3 of the x. When you multiply them all together, you notice that there's now 5 copies of not just the x, but the 3 as well. So you have 3 times 3 times 3 times 3 times 3, okay, which gives you, when you simplify, 3 to the exponent 5, x to the exponent 5. So that exponent winds up applying to both the 3 and the x. You notice that this is not true if the two values in here are added together. Okay, then it's a binomial they have to expand using an array. But these two values are multiplied together, all to the same exponent. You wind up with 3 to the 5, x to the 5. So again, note there that the exponent applies to both the x and the y. Okay, the same holds true for division. The exponent will apply to both the numerator and the denominator. Again, just for an example of seeing that in action, let's say you have 2/3 the exponent 5. Okay, that's 5 copies of 2/3. Multiply all the 2's together, multiply all the 3's together, and you wind up with 2 to the 5 over 3 to the 5, which you can also simplify a little bit further, but just seeing how the exponents distribute there. Okay, so these are the 5 exponent rules you would have seen way back in grade 9. And you've used them a little bit since then, mostly when doing algebra, but they're going to come back. We're going to make lots of use of them now. Okay, so with that in mind, let's try thinking back to the table we did up here. Okay, try and come up with some new laws for negative exponents and for 0 exponents. Okay, so one thing I want to look at here, for anything to the exponent of 0, going back to our table here, what happened when anything exponent 0? So that happened once in each chart, here, here, and here. And what you notice is that every single time it was equal to 1. Okay, so anything to the exponent of 0 is going to be equal to 1. Can you probably believe that's true based on having seen it in all the tables of values that you just did, but just as a further explanation of it, let's say we're looking at the case we have 5 to the exponent 5 divided by 5 to the exponent 5. Okay, so basically something divided by itself. So if you were to write this all expanded out, you'd have 5 to the 5 over 5 to the 5, which gives you, again, 5 5s over 5 5s. And you know that there's going to be lots of canceling going on here. Every single pair of 5s here is going to be canceled out. So when all is said and done, you're just left with 1. Okay? if you want to use the exponent laws, the division rule is telling me that when I divide two powers of the same base, I subtract the exponents. This is the same thing as 5 to the exponent of 5 minus 5, which is 5 to the exponent 0. So since both of these are equal to what we started with, what we're saying is 5 to the exponent 0 equals 1. You can apply this to any base you have, as long as the exponents are the same there. They'll simplify to something the exponent 0, and it's going to be equal to 1, because again, it's just going to be something divided by itself. Okay. Now, as for the negative exponents, again, we briefly talked about them here. You'll see that when you have 2 to the exponent 3, it's 8. 2 to the exponent negative 3 is 1 over 8. And so it's equal to the reciprocal of what it was when the exponent was positive. You see that holding true for everything else. 2 squared and 2 to the negative 2 are reciprocals. 3 to the negative 3 and 3 cubed are reciprocals. 2/3 to the exponent 4, well, we don't have the negative 4 on here, but 2/3 squared and 2/3 to the negative 2 are also reciprocals of each other. So what we can actually summarize then is that x to the negative n is going to be equal to 1 over x to the exponent n. Okay, so what this would mean, for example, let's say you have 4 to the negative 5. This would be equal to 1 over 4 to the positive 5. Okay, if your base is a fraction, it's still the exact same idea. Okay, take the reciprocal of that base. Basically, if you want to make it a positive exponent, you can flip that base and make it in a positive exponent. Okay. Similarly, what you can do is then, from there, apply the exponent to both numerator and denominator, and wind up with y to the n over x to the n. Okay, so the general rule of thumb is if you have something to a negative exponent, if you take the reciprocal of the base, it now becomes a positive exponent. So again, let's say we had 4 over 5 to the exponent of negative 6. This would be the same thing as 5 over 4 to the positive 6, which in theory you could take further and say this is 5 to the 6th over 4 to the 6th. Okay, so these are the new laws that we're going to be looking at in grade 11. Okay, so if you want to just, in case you didn't believe me about the negative exponents, take a look at another example that might be illustrated for you a little bit more. Let's say we have 5 to the 5 divided by 5 to the 7. Doing exactly what we did with the other case, if we write it all out in expanded form, we have 5 5s divided by 7 5s. And you'll see there's going to be some canceling. And what we're left with is just 1 in the numerator and 2 5s in the denominator. Okay, so it's going to be 1 over 5 squared. Using our division rule, we're going to subtract the exponents, so it's going to be 5 to the exponent of 5 minus 7, which is 5 to the negative 2. So 5 to the negative 2 and 1 over 5 squared are the exact same thing. Okay, there's another way of illustrating that rule. Okay, so some other things to look at. All these exponent rules that we looked at, and I mentioned this earlier, if you have two values in a bracket that are added together, i.e. a binomial to a certain exponent, you cannot distribute the exponent. That is the most common mistake I probably see with algebra. So the kind of mistake we probably all did at one point back in grade 10, x plus 2 all squared is not equal to x squared plus 4. Okay, absolutely not. What you would have to do is use an array. Okay, you go x plus 2, x plus 2. Okay, and then you'd fill in your array with multiplication. Okay, so it's actually x squared plus 2x plus 4, not x squared plus 4. So do not distribute the exponent there if the base has two terms that are added together. Okay, so other thing that comes out that you have to think about, negative 3 squared is not the same thing as negative 3 squared. There's a very subtle difference here. In the first case, the negative is not squared. Okay, so you have negative being left alone, then 3 times 3, because only the 3 is squared, so you get negative 9. On the other one, the negative is in the brackets, so it's also squared. So it's negative 3 times negative 3, which is positive 9. You have to be very careful about this, because sometimes your calculator will automatically add the brackets. So if it's doing that, you have to actually recognize that if you're given something that just says negative 3 squared, you have to know that this means that the negative is not included and write it out as negative 9. Your calculator might actually tell you it's positive 9, so you have to be careful. Okay, and last thing with this one, just the terminology. X to the n is referred to as a power of x. So the whole thing's a power, and n is called an exponent. Okay, we'll start doing some examples in part 2, and we'll see you over there.